us consider a circuit consisting of an inductor in series with a resistor R. Let us say this is supplied by a constant DC voltage source V. The current into the inductor is ILT. From the circuit theory, we know that the current expression through an inductor is equal to the voltage divided by the resistance multiplied by 1 minus e to the power minus t by tau. Here the tau is a time constant which is defined as the time taken by the current from reaching from 0 to 63% of its final value is termed as the time constant. The current profile we can plot here as this. It rises exponentially and reaching to certain fixed constant value which is equal to the voltage source divided by the equivalent resistance of the circuit. So this is inductor current versus time. So the amount of time taken by the current to reach from 0 to 63% of this final value is taken as the time constant here. But please make a note here that a practical inductor does not have a perfect inductance value. I mean to say that apart from its inductance there exists some parasitic resistance which is termed as equivalent series resistance. So where does this come from? Actually, when an inductor is wound using some copper wire, so this is copper. The copper or any material does have certain kind of resistivity, that is the property of the material. So depending upon its dimension, which is length and cross sectional area, we define the resistance of a wire. Let us call this RL is directly proportional to the length upon the cross sectional area of that wire. So that also depends on the number of turns multiplied by length of one turn divided by area. So that comes from that material. So therefore in that case the equivalent time constant is considered, which is equal to the inductance value divided by the equivalent resistance, which is RL, which is the ESR or parasitic resistance of the inductor, plus the load resistance, or we can say this series resistance connected here. So what is happening here? If we notice the current profile here, the current is increasing not non-linearly, which is exponential in nature, and it is reaching certain constant value which is V by R. So for the time t very greater than tau, we can consider that this is having a fixed current value which is nothing but V by R, meaning in the steady state this inductor is not opposing any current and the current is becoming constant, which depends only on the resistive value of the circuit but not on the inductance value. Whereas before the steady state we notice that the inductor current is rising slowly and exponentially, which depends on the time constant tau, which is the function of inductance, and the equivalent resistance. Let us consider another circuit which consists of a charged inductor, and this is connected to a resistance R. So earlier this was connected to this voltage source V, and now this is connected directly to this. Okay, so this was connected to the switch S1, and now this is connected to S2. Let us say consider the time of switching instant of S2 is let us say equal to T1, which is larger than tau. Okay, time constant. Now what happens when the switching transition happens from S1 to S2? Initially the current through this inductor was a fixed value, which is V by R, but at certain instant abruptly we are switching the node from S1 to S2, and at that particular moment this current is having certain current, or in terms of energy we can say that it is having certain amount of energy. As soon as we switch the position of switch from S1 to S2, the inductor current cannot be interrupted abruptly, as we know that inductor has the property to oppose the current change. It cannot allow the sudden change of the current. So it will not become zero, rather it will continuing supplying energy to this resistance value. But in this circuit there is no not any energy source, as unlike the earlier case which was having a voltage source V, and it was consistently supplying energy to the inductor and the resistance. But here in the second case there is not any independent voltage source or independent energy source which is providing energy, rather the inductor is behaving as an energy source, and this is supplying energy to the resistance R here. So what is the expression of the current? So we can write ILT is equal to I naught, which was the initial energy of initial current of this inductor L, and this will be e to the power minus t by tau, or rather say we can tau equivalent. So this is the current expression. So what is the value of I naught here? This I naught is the initial current. So what is the initial current? Let us say at time instant t equals to t1, let us consider this as t1. So what is the value of current at this particular instant, which is V by R. Therefore I naught is nothing but V by R. Now let us draw that current profile combining these two cases. Earlier it was the inductor was building the energy, and the situation was like this. At time instant t equals to tau 1, sorry, t equals to t1, which was very greater than tau equivalent, we abruptly change the position of switch from S1 to S2. Therefore rather it will start decaying in the same fashion but in opposite direction. So we can simply represent the current like this. At infinity, meaning that the current will start approaching towards zero value. So this was around 0 ampere in for very longer duration. So this was the time axis, this was the current axis, this value was V by R. Now this is decaying. Okay, So during this portion, the energy, the inductor was charging, and during this stage, inductor was discharging. From here we can understand that inductor has a property to store and release energy, which depends upon the configuration of the circuit. The mechanical analogy of an inductor is uh, a spring. So this is the inductor. The mechanical form, we can say that a spring is connected to a mass m, and whenever we push in this spring, it stores energy, and when we release it, when we remove the external pressure, let us say this is external force. When we release this external force, it exerts the outward force according to because it exerts it releases its stored potential energy and converted to the kinetic energy. In a similar fashion, when we charge the inductor current, it starts building its energy and reaches to certain value depending upon the circuit configuration with certain time constants. And when we allow that inductor to discharge, it releases its energy further to the load or to the dissipating element, and it may also be another storage elements like capacitor. So this is the analogy of electrical inductance and mechanical spring. Now consider a situation where this switching of S1 and S2 starts happening very rapid, meaning that this switch swings in between S1 and S2 with very high speed. So what will happen? Let us say initially the inductor was fully charged, and then it was allowed to discharge, and then again it is connected to the source voltage V, and then again it starts discharging to the resistor. So how will that current profile look like? Let us say this is a switch, this is another switch, this is inductor, this is resistor. So initially let us say the inductor current is at this value I naught. So let us say this is switching instant T1, another switching instant T4, and so on. Okay, so at t equals to T1, allowed to be connected to S2. Okay, so it will start decaying its energy. We are assuming that initially the current through the inductor was I naught, therefore so it will start decaying with a time constant tau. But it was not, let us assume that the time constant is very greater than this switching instance, which is uh, T2 minus T1. Then what will happen? If this time constant is very high, then it will not fully discharge, or it will not discharge up to 37%, rather it will discharge up to certain extent, and is at that particular instant the energy in the inductor is not fully, it is having some non-zero value, it is not completely discharged. Let us say this is I1. At that particular instant, we throw the switch again back to the position S1. So this inductor will be reconnected to the energy source V, and it will start building its energy again as earlier. So the current will again start increasing tau. So the inductor current will start increasing because it is rebuilding its energy and as supplied by the independent voltage source V. Again at time instant t equals to t3, we throw the switch position from S1 to S2 and it will start decaying its. Okay, this will keep continuing in this fashion, and the inductor current will look like this. Now let us say if this time intervals, say from t2 minus t1, t3 minus t2, if this instant t4 minus t3, if these time intervals vary less than the time constant tau, then we can approximate this nonlinear behavior of the current profile, which is exponential in nature, and this can be approximated as linear profile. So if uh, this instance starts decreasing, let us say like this, then the current will decay from here to here, and it will again start rising from here to here, and this will be further continued. So what we are seeing, with this assumption, the current ripple, I mean the peak to peak value, is decreasing delta IL in case in light of this assumption. And if we increase these intervals further, we will notice that the time difference, the current ripple will be higher in inductor current, meaning the current has to swing between a larger range of current from I1 to I0, and as uh, the time intervals decreases and becomes very less than time constant tau, the inductor current ripple will further fall down. Why this concept is important? This concept is important to understand the behavior of power converters such as buck converter, boost converter, and other kinds of converters, because inductor and capacitors are considered as the building blocks of this type of converters, which stores and releases energy, or sometimes it starts resonating its energy uh, from one end to another, and with the help of that we can convert the level of voltage from input to output. We can either increase the voltage or we can decrease the output voltage, and they are called the boost converter and the buck converters respectively. So these are the basic building characteristic inductor current profile, and based on that we can understand uh, the behavior of inductor, and we will be using this concept to understand the circuit analysis and the behavior of uh, buck converter first, and then after we will see same about the boost converter. Okay, thank you.